Let's start today's lecture. Today's theme related to yarn unevenness. It's evident that we need to use a lot of probabilistic and statistic tools for analysis of such problem. We will start about so-called Martindale's theory of Professor Martindale, and then I want to introduce some newer model based on bundle character of fibrous material. Let's start with the easiest version with Martindale's theory. Our general assumptions are following. All fibers are straight and parallel. Let's imagine it so. Parallel to sliver axis, of course. All fibers have same length. We call it L. All fibers are positioned along the sliver individually and randomly. When we accept the idea of so-called binomial sliver, we need also say the assumption length of fiber laid down is finite. Yeah? The situation is shown on our picture here. L, it is a length of each green fiber. Capital L, from here to here, this length, this straight line, it's laid down length of fibers, right end of each fiber is shown by this yellow point. Our idea, or Martindale's idea, is following. If a fiber passes the position A, then the right end of this fiber must lie within the abscissa, within the part from A to A dash. Is it shown? If the fiber like this here have its right end in the distance from A to A dash, then covered the point A or elemental interval here. When no, for example, this fiber or I don't know this fiber, then don't cover our point A. Probability of passing the point A by a random fiber, it's evident. It's small l length of fiber by capital L. Why it is? Oh, because possible is to lay in the interval from A to A dash, and we can be sure that our fiber, which we gave inside of the length capital L, must lie in the length capital L. So that the probability here is small l by capital L. N is total number of fibers which we gave to our length capital L. We call N1 I can say average number per unit length. It means number of all fibers by our length L. Number of fibers related to unit length. How is the probability that just small n, which is smaller than number of all fibers, capital N, so the probability that just small n fibers passing the position A. Now it means small n fibers passing the position A and capital N minus small n fibers don't pass. Sure. Well, it's evident that the distribution of a number of fibers covering the position A must follow the binomial distribution It's evident from your first lectures about the theory of probability. Binomial distribution. And you know about the binomial distribution that it is valid, that for example the mean value of binomial distribution n bar is capital N times P, number of all fibers times probability. It's derived in disordered handbook about the theory of probability. Or alternatively we can write n bar is capital N times P, but n is n1 times L. And P, it's small l by capital L. So that we can write it also in this form, and or n bar is n1, capital N1, number of fibers, average number through related to length unit, times fiber length. Well, but also we know it from earlier lectures, number of fibers in cross section is generally capital T to small t times Kn, count, or better fineness of our bundle by mean by fineness of fiber times our known Kn factor. Because parallel fibers, Kn must be equal 1, and so that n bar is capital T by small t both bar. Variance. Variance or dispersion of number n, number of fibers covering the point A, is based on our statistical handbook n times p times 1 minus p. Or this variance is also n times p is n bar, and probability we can write as n bar by n, as we shown. Well, coefficient of variation, which we in theory every time use as a dimensionless quantity. So now, for example, 15%, then 0.15. And this coefficient of variation, this is given by known ratio, square root of variance by mean. Using our equations, we obtain this expression for coefficient of variation. Yes. Fibers, this is coefficient of variation of what? Of number of fibers. Of number of fibers. N. Vn. Number of fibers. It characterizes the variability of number of fibers. But usually each fiber have a little other own fiber fineness. Therefore, we must study coefficient of variation of mass irregularity, no number of fibers irregularity. Fibers in a sliver cross section are from, there are n, small n fibers. Let's have some subscript for each fiber. I is 1, 2, 3, and so on to n. Fiber fineness. Fineness is now T1, T2, T3 to Tn in our section of sliver. Coefficient of variation of fiber fineness we will call Vt. Variation of T, no, and then T. Fiber fineness. Dimensionless, of course. Let's now imagine our infinitesimally small distance dx in our scheme. If number of covering fibers is equal to 0, then evidently the mass in our small, differentially small length is 0. When no, then mass dm from all fiber elemental parts in our elemental distance dx is which of? No, mass per general height fiber is Ti times length, so the Ti times dx. Sure? Yeah. And because dx is common for each fiber, for all fibers, so that it is dx times sum for I equal 1 to n of Ti. If n is 1, 2, and so on to the n. How is the count, the fineness, the local fineness of sliver in our elemental portion dx? How it is? It's the mass by length as each fineness. It is 0 if n equals 0, if number of fibers is equal to 0, and its dm by dx is dm is this one by dx, so that it is sum of Ti for n equal 1, 2, and so on to then. Yeah. T, you can see that the quantity T, the local sliver fineness, is a random quantity from 2 points of view. First, number of fibers n is a random variable following in this moment a binomial distribution derived before. So that n here, from 1 to n, this n here is a random quantity. And second, each fiber fineness, when we have more such differential layers, the first fibers in different elemental dx lengths have some distribution. T1 have some distribution, T2 have some distribution, and so on. So Ti is also a random variable. Nevertheless, because from the same material, having the common coefficient of variation Vt. Is it clear? Therefore, from 2 points of view, because n is random and each Ti is a random quantity, also the fineness of the sliver, local fineness of the sliver, must be a random quantity. We haven't enough time to derive some probabilistic relations. Therefore, let me, in short, inform you about the possibility, what is possible to derive in theory of probability for one special type of random quantity. So now we are not in textile problems, now we jump to some statistical handbook or statistical teaching book. Yeah? Let's imagine a random quantity y, defined here. Y is 0 if some quantity m is 0 and y is sum for 1 by m xy from xy if m is 1, 2, 3, and so on. Sum of this value. Let the random variable B exist. M is discrete random variable with mean value of this Em. You know that for mean we usually use some operator E. So Em is the mean value of random quantity M, and variance of M is dm. Dispersion. Each x is also random variable with a common mean value. Each exe is equal to ex, only one quantity, and common variance, each dxi is equal to dx, only one value. And therefore also common coefficient of variation vxi is some Vx common for all fibers, first as well as fifth, as well as 13th, and so on. Well, when we derive the coefficient of variation of such a random quantity, using the tools from theory of probability and mathematical statistics. Finally, we obtain this equation. Let's believe me it. When no, please find this, for example, our book about the structure of fibrous assemblies as an attachment, as an appendix in this book, it is derived. Professor Ishtiaq have this book in his library. Well, what is it? Square root of coefficient of variation of such a random quantity y is 1 by mean of m times square root of coefficient of variation of x plus variance dispersion of m by mean value of m. So this is the result from theory of probability. This expression we will use more times today. And now back to our problem. The coefficient of variation of local sliver fineness was this here, yeah? But this is random variable type y. Therefore, we must use such general formula for evaluation of coefficient of variation. Now, especially on the place of y is capital T, on the place of m is small n, on the place of em is evidently en, mean value, is n bar, you call it n bar, on the place of d, dm is dn, and we call it sigma square n, and on the place of each xi, we now use the ti, and of course on the place of vx, in general formula we have now especially vt. What we obtain applying our result from theory of probability, this equation, it's this equation, yeah? Because we derived sigma n or sigma n square, this is from binomial distribution, and n bar, which is n times p, we obtain or this the same, yeah? For square of coefficient of variation of local sliver fineness. Because it was derived n bar is capital T bar by T bar ratio of mean values of sliver fineness and fiber fineness. The coefficient of variation of local sliver fineness is Vt. I use this equation, this equation, and we obtain this here. Where the probability P is given by this or this, how you want. Yes. So it is by binomial distribution. We need to know the mean value of sliver fineness, of fiber fineness. We need to know the value of coefficient of variability, coefficient of V for fiber fineness, coefficient of variation, of course. And we need also to know the parameter P. It was discussed earlier. It related to length capital L, which we used in our starting idea. Especially the parameter P is difficult to formulate. Nevertheless, usually we can imagine the process of creation of sliver as a process which is actual on a very long length, capital L. Therefore, let's imagine that the length of fiber laydown length, capital L, limits to infinity. It's very, very long and limits to infinity. The total number of fibers, capital N, it's also limited to infinity. Yeah, it's higher and higher and higher. Nevertheless, the number per unit length, N1, which was number of all fibers by length, remains constant. As constant. Yeah? So that I elongate, I don't know, capital L 10 times, and number of fibers I increase also 10 times, so that N1 stay be same. It's mean number of fibers per length unit. Yes, how is the consequences of this one? A mean value of fibers in a sliver cross section, small n bar, we derived is N1 times L. N1 is stable, L is stable, so that N is constant, no changed. Nevertheless, the probability P, which was small l by capital L, when L is higher and higher, when increased to infinity, is a limit of this ratio, and because L is limited to infinity, then this ratio is limited to 0. The probability P is limited to 0. Therefore, I can use this expression in the special moment in which the P is equal 0, and I obtain this equation. This equation corresponds to this limiting, is the limiting from binomial to Poisson distribution, so that we call, usually we speak usually about the Poisson sliver, and this equation corresponds to the I can say natural unevenness of Poisson sliver. Yes. By the node by Uster notation, you know what is it, Uster? Instrument Uster tester, and so on. By Uster notation, the value Vt is known by the so-called limit irregularity with symbol CV lim in the material of this company. What we need? We need to know the coefficient of variation of fiber fineness. Nevertheless, usually we haven't it, and it is difficult to directly to obtain. Therefore, we can use some approximation and apply no coefficient of variation of fineness, of fiber fineness, then fiber diameter. How? Coefficient of variation of fiber diameter is now our theme. Let's show that D, let's think that D is equivalent fiber diameter. Fiber diameter we derived is 4 times D by pi rho. D bar is mean value of D, fiber diameter, and sigma square D is variance of fiber diameter D, and Vd is coefficient of variation of fiber diameter D. It is valid, this is one of our first equations. It is valid that T, fiber fineness, must be pi rho by 4 times D square, because D square or something, so you know it from lesson 1. So this relation is valid. This expression is valid. This is not function of D, so let's for short make short our formal graphic form. Let's call it a sum parameter k. K times D square. Okay? Make a derivative of this equation so that we obtain dt by d is 2kd. Sure? Yeah. And using Taylor series of fiber fineness, it use around d bar. You know what is a Taylor series? Yeah, I think yes. You heard it, minimum. Okay. We obtain some series which is t is k times d bar square plus 2k d bar by 1 factorial times d minus d bar plus and so on and so on. This is this here. Let's say our approximation will be enough when we will use first two members in this series. Therefore, let's use t is 2k d bar d minus k d bar square. When you use it, then we can, from this equation, to obtain mean value of t. What is it? Mean value of this here. This is absolute. It's evident that this is k times d bar square, because you obtain 2 times it here minus 1 times it. Variance, it is a d from this expression. The random quantity is this d, this here. And because constant don't play a role, and the parameter 2k d bar by variance of some constant times random quantity is the constant square times variance of this random quantity. You know it from probability, theory of probability. We obtain this here, so that square of coefficient of variation of is which of coefficient of variation of t was sigma t square by t bar. But sigma t square, what is sigma t square? Sigma t square, it is here, by t bar square, it is this here, from here. And so after rearranging, we obtain Vt is 2 times Vd. On the place of coefficient of variation of fiber fineness, we can roughly, because this is approximation, we can roughly write 2 times coefficient of variation of fiber diameter. Well, so our equation have now such form. It is the final equation for us in the moment. And same equation you can read in the professional material of Firma Zellweger from Uster, Switzerland, in such form, because in percentage and so on, therefore this 0.00. Okay? So we know why it's here, this number 4. It's because this way, this approximation of coefficient of variation of fiber fineness. Well, this is all for, in the moment, for sliver having parallel fibers. Let's solve the theoretical case. Practically, I don't imagine how it is possible in technological process to realize, but a theoretical sliver where each fiber, like this, created like this here, based on this scheme, where each fiber have same angle, theta angle, to longitudinal direction of sliver. Each fiber is an oblique fiber having the same angle theta to longitudinal direction of sliver. The scheme, I think, can show you what is our theoretical imagination. One fiber seems like this here. Now, let's imagine that I cut this fiber to very short elements vertically, perpendicularly to longitudinal direction of sliver. Here, 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 and so on. Whole fiber. I cut to a lot of very small such fiber segments. And now the fiber segments remove to this position, and I glue it together. Can you imagine it? Then what I obtain? I obtain a fiber, a new fiber, reconstructed fiber, hypothetic fiber, imaginary fiber, having length L star, having another fiber fineness T star, another fiber cross-section S star, but this fiber is parallel. This fiber is parallel with longitudinal direction of yarn. Of sliver direction, isn't it? Let's calculate this parameter of our imaginary fibers, reconstructed fiber. Angle theta is constant, so that length from this picture is evident that the new length L star, it's L times cosinus theta, a trivial geometrical triangle. S star, we know it from earlier lectures, S star must be S by cosinus theta. Fineness of imaginary fiber T star, we know that fineness is cross-section times rho. Now cross-section of our imaginary fiber is S star, and for S star we know this expression shows that S star times rho, S rho by cosinus theta. And because this S times rho is T, starting value of fiber fineness, we obtain that the T star is T by cosinus theta. Is it well? Yeah. And we reconstruct our oblique fiber to another fiber which is parallel to sliver axis, and we can use the same quantity as earlier. Also V square T bar, we can say it is the same. We derive using equations which we derived in last slide, and we obtain finally, because by cosinus square by cosinus square, so that we obtain that V square T is same as V square T star. The coefficient of variation is now changed after our hypothetic cutting and rearranging of our fibers. Well, because same, we can use also the same equation. Our equation in Poisson sliver was this black here. Only new is that I have here on the place of TT star, and on the place this in here too. Well, but we know that T star bar is T star by cosinus. The same, this is equivalent with this. So I obtained finally this equation, isn't it? You can see that here the angle theta plays some role. It is in the denominator of this ratio. So that coefficient of variation of local fineness increases with the increase of the oblique angle theta. If our theta in starting graph is increasing, then cosinus is decreasing, and 1 by cosinus is increasing, so that Vt is increasing. The shape, the angle theta, play a role to the final sliver irregularity, to the final variation coefficient of variation. Yes, our earlier case was pure theoretical, to have the sliver with constant angle theta. It's only theoretical idea. Nevertheless, in a real sliver, we have a lot of directions. We can imagine that our final sliver is results from doubling of lot of partial fiber slivers, and each partial fiber sliver have same angle theta. Yeah. So let's now imagine the idea of doubling of Poisson slivers with oblique arranged fibers. We have m individual slivers. Subscript 1, 2, 3, and so on to m. Each sliver have, for example, the first sliver have the mean sliver fineness T1 bar, mean fiber fineness small T1 bar, coefficient of variation of coefficient of variation of fiber fineness V T1, angle oblique angle theta 1, and length of fibers L1, and so it is in all slivers. So it is in all slivers, and so that we can formulate the coefficient of variation. Coefficient of variation of local sliver fineness of generally a jade sliver. J is from 1 to m. It is our known equation, nevertheless with subscripts j. Here is subscript j here as well as here, because it is jade sliver. The square of VTJ is this here, evidently. So variance is this here from this equation. Variance is this here, and we know this V squared Tj here, from earlier. VTJ is here. So using it, we obtain this expression for variance in a jade sliver. It is well. So the variance is finally this here. And you know that it's valid for the doublet sliver, that the resulting mean value T bar is sum of partial mean values Tj bar. And variance is sum of variances. Using these expressions, especially for variance, we obtain, because Vt is this here, square root of dispersion by mean value square, we obtain dt using the equation derived in last slide. We obtain this here, and for coefficient of variation of fineness of doublet sliver, we obtain as each coefficient of variation, we use this expression here, so that this here, and finally we obtain this expression. The angles theta j play some role, so that the orientation of fibers plays some role for final coefficient of variation Vt. If the distribution of this angle is relatively very significant, then also we can see that the coefficient of variation of local sliver fineness is increasing, because in denominator are these quantities. Let's remember that the ratio Tj bar by T bar, it's Gj, which was the mass ratio of jade individual sliver. Yeah, this ratio here have the same as a mass ratio of jade sliver in whole sliver. Well, this is quite general equation. We can solve some, maybe 3 special cases using this. The easiest case is, in each partial sliver, the length is constant, is same for each fiber sliver. Mean fiber fineness is same. Coefficient of variation of fiber fineness is same. The angle of the oblique angle, the angle of fibers in relation to longitudinal direction of sliver, is same and equal 0. What is it? It's the parallel fiber bundle, or earlier. You can use our, it is for checking, of course. You can use our equation, which is here, and based on this values, after small rearranging, you obtain that it is this here, our earlier starting equation, isn't it? Well, we have not some mistake in our, some formal error in our equation. It's also as a checking of. Second, mean fiber fineness is same. Coefficient of variation is of fiber fineness is same for each slivers, partial slivers. Angles are same and equal 0. Nevertheless, I said nothing about the fiber lengths. Maybe that each partial fiber sliver have another fiber length. Nevertheless, the length is not in our equation. We can have, and the coefficient of variation is not changed. Fiber length is not in our right-hand side for coefficient of variation of local sliver fineness. Length of fiber don't play a role for our value Vt. So that we obtain same results. We show that the length is not important for coefficient of variation. Third, fiber length doesn't affect the sliver unevenness. Third is here, fineness is constant, third special case. Mean fiber fineness is constant, coefficient of variation is constant, but different about the angles. I didn't say that they are 0. Each angle can be another. Yeah? Well, then I obtain, using our starting equation, such equation from which is evident that the fiber non-parallelization increases the unevenness. The unevenness is best for parallel fiber bundle, parallel sliver. For non-parallel fiber slivers, the unevenness is increasing because the cosinus theta e, this is a sum of some expressions having cosines of theta j in denominator. From this it is possible to see. It's not necessary every time speak about calculation or calculate numerically it. In your industrial praxis, it's also possible to understand why is this result, and to know that when you have too high distribution of fiber angles, to significant distribution of orientation, fiber orientation, it can influence to final value of an unevenness, isn't it? Yeah? Well, to the end of this lecture, I want to postulate Hubert's index of irregularity. It was theoretical concept based on binomial, later Poisson's sliver, and we obtain some equations. From other side, we are able to measure sliver or yarn unevenness, yarn irregularity, using maybe the knownest instrument from Zellweger-Uster, so-called Uster tester. We obtain two values. One is practical value, measured value of uneveness. I call it as effective. And second is the theoretical value which we derived. We can create such a ratio, real to measured to calculated. It is known under the term Hubert's index of irregularity. Index of irregularity according Hubert. It's name of author. In Usta material from this company, they call it CVF or CV-lim. Yes. Value of this index based on practical experiences is in large diapason from maybe 1.2 to 2.5 sometimes also. It's very high value. This difference between our theoretical result and the result of experiment is very high. It is not 5%, but for example 50%, 80%, 100%. We calculate, I don't know what, some value, and the reality is 2 times higher. It means that something in the Martindale's theoretical concept, we have not some influence, something is false, I can say. What's false? Some influence, which influence to our final experimental values of unevenness, we don't have in our model. We must make some corrections. Therefore, we in Liberec made some corrections, and about this newer or modified model, I want to speak in our next lecture. Yes, in this lecture it's all. Thank you for your attention. Be happy and see you in our next lecture. Bye.